Okay, hello everyone. Welcome to the best session in the entire conference. I have to say that because this is the TOPL session. It's literally touching my mask. Yeah, okay. So some years ago, as you know, TOPL is the premier journal in programming languages. Apologies to JFP. Some years ago, we started this journal first process where people could submit things to TOPL and request to present at one of multiple conferences. And so one of the things that I instituted was to get POPL added to that list of conferences. And so we've been seeing an increasing number of great submissions coming in to TOPL where people are also saying, well, this is fresh new work, not an extended version of something previous, and we'd like to present it at POPL. So indeed, that has been happening, and this year we have enough papers that basically we have a whole session of these papers. So as I commented earlier, what maybe the session lacks in thematic coherence, it makes up in quality. But actually there is a certain amount of coherence because two of the papers are very much concerned with concurrency. But the third paper is on another topic, but also very interesting. Two of the first two papers in the session have already come out in TOPL, I believe, and the third one has not quite made it into print. It's been accepted, but I think it'll be in the next issue. So you can find that there very soon. Okay, so our first speaker, I believe, is Jade Alglave, talking about formal concurrency modeling at ARM, and I will hand the floor over.
Hi. So, yes, thank you. This is joint work with Will Deacon, Richard Greenthwaite, Antoine Lacar, and Luc Marangé. So to start with, let me say a little bit about ARM architecture. So ARM develops architecture specifications, by which I mean the envelope of allowed and forbidden behaviors that all ARM implementations must agree with. Another way of saying the same thing is that the architecture describes what software can rely on coming from any piece of ARM hardware. As an example, here's the litmus test. It's called, the title of it is MP for message passing. Between the curly brackets, you can see the initial state, and here the columns describe threads P0 and P1 that communicate via shared variables X and Y. So very quickly, the syntax says that P0 writes 1 to the data X, and then updates the flag Y with value 1. P1 reads the flag Y, and then reads the data. And the exist clause here at the end asks a question about the final state and asks whether there is a scenario under which the reading thread P1 can get the flag yet read the stale data from the initial state. And the architecture decides if the behavior is allowed or not, and in this particular case, the behavior is allowed. So deciding whether such litmus test is allowed or not is a question of architecture, but more precisely a question of the memory model. And since 2016, we formalized the memory model of ARM. The effort was started by Will. We write the memory model in a DSL called CAT, which has a formally defined semantics. Therefore, all the models written in CAT are formal models. And in addition, this DSL drives a collection of tools. The herd tool is a simulator that takes as input a CAT model, so a memory model, and a litmus test, and returns the allowed outcomes of that test under that model. The DIY tool generates systematic families of such litmus tests, and finally, the litmus tool runs those tests on hardware. So here's the MP test we've just talked about, and here's a sibling test where I've added fence instructions. So here DMBST between the two stores ensures that those two stores won't be reordered, and here DMBLD between two loads ensures that those two loads won't be reordered. As a consequence of using those fences, the behavior where the reading thread gets the flag but reads the stale data is now forbidden by the architecture and the memory model. So the way we do this in the ARM memory model is the memory model lists a certain number of ordering requirements over memory accesses, and it does so by forbidding certain shapes in program executions. More precisely, usually we forbid cycles. So one of these axioms is called external visibility, and it requires that there is no cycle in what's called the ordered before relation. The ordered before relation is made of two sub-relations. One of them is locally ordered before. It concerns the local orderings within a thread, so everything that is due to dependencies or fence instructions, for example. And the other sub-relation that constitute ordered before is called observed by, and it corresponds to the interactions between threads, so the communications between threads. Here's the bit of cat that describes the axiom. We ask that there are no cycles with the keyword acyclic. LOB stands for locally ordered before, the pipe is the union, and ob stands for observed by. So here we're asking that there are no cycle in the union of locally ordered before and observed by. And applying this to the examples we've just talked about, so here's the execution that corresponds to the unfortunate message passing scenario, the one that is allowed where we get the flag but read the stale data. So you can see the initial state here, the two writes of x and y with value 0. Here you can see the semantics of the writing thread. We've got the write of the data with value 1 and the write of the flag with value 1. The program order arrow PO here just says that those events come from instructions that were written in that order in the program. Here we've got the semantics of the reading thread. So we've got the read of the flag y with value 1 and the read of the data with value 0. The red and blue arrows are the interactions, what I call the interactions between threads, the observed by relations. So for example, the read of the data here takes its value from the initial state over there, and we have a read from arrow to signify this. Similarly, the read of the flag here takes its value from the update of the flag made by the writing thread, and we have a read from arrow here to signify this. Finally, the read of the data, the read of the stale data is overwritten, rather the value, the stale value is overwritten by the update made by the writing thread here, and we have a coherence arrow, that blue arrow, to signify this. So now if we go to look at the sibling test, the one with the fence instructions, the extra arrows that we have here are the locally ordered before relations that are due to the fence instructions are placed between the two writes and between the two reads here. So now we've got, as you can see in this execution, a cycle in observed by and locally ordered before, and this explains why that behavior with the fence instructions is forbidden. If we go back to the behavior without fences, we've not got the locally ordered before relations on each thread, and therefore we've got no cycle, which means that the behavior is allowed. So starting from this background, we present several contributions. So the first contribution we present is we give two alternative formulations of the memory model that are also implemented as CAD files. So the original memory model, the one I just gave a brief presentation of, requires a whole system view of program executions. But a CPU designer might want to design, might want to have a per core process of design, which means that if they want to understand whether the memory model applies to the machine they're designing, they would have to work out for themselves how those constraints translate per core. So the alternative definitions that we provide spare them that effort and allow to reason about the validity of an execution from the point of view of one core and not the whole system. We also provide an extension of the ARM memory model to mixed size accesses. I'll expand on what that means in a second, but the motivation for this in particular is without such an extension, constructs within the Linux kernel cannot be used only on ARM machine, and I'll give an example of that in a bit. We also provide an extension of x86 to mixed size accesses. So I will focus exclusively on the extension of the ARM memory model to mixed size accesses, but obviously the details of the other contributions are in the paper. Right, so focusing to mixed size for ARM. So here's a mixed size scenario to explain what I mean by this. So we have two threads, P0 and P1, that communicate via a 16-bit wide variable x, as indicated in the initial state. P0 does an 8-bit store of x, that's in yellow here, writing 1 into the least significant byte of X. And P1 does a 16-bit store to X, writing 2 in each of the 8-bit halves of X. And if P0 does a 16-bit load of X, the question we're asking is, what values can it see? Can it see the 2 halves of the long store, or half of the half written by the short store, or a combination of both? So that's that sort of question that we aim to answer with our extension. We could think of several pathways to extend, backtracking a little, we're focusing exclusively on multi-copy atomic models such as ARM and x86. And those models essentially create a taxonomy of relations. So those relations are either the local orderings preserved by the architecture, so that's locally ordered before for ARM, or the orderings that are relative to values taken by one memory location. So in ARM, that corresponds to a relation that's called local write successor, and the observed by relation that I mentioned, that's the communications between threads. So with that taxonomy in mind, we could imagine 2 pathways to extend multi-copy atomic models to mixed size accesses. The first one is when 2 events are locally ordered with, for example, locally ordered before, then the sub-events generated by the same instructions benefit from that local ordering as well. The other pathway is when 2 events are ordered by a communication relation, then similarly the sub-events generated by the same instructions also benefit from that ordering. So let me give an example to make that a bit more concrete, and also explain why one of those 2 pathways cannot be taken. So it's again a variation on the message passing idiom. We've got 2 stores on P0. The first one is a 8-bit long write to X. The second one is a 16-bit long write to Y. And in between them, I've placed a fancy instruction DMB. So semantically, this corresponds to this. You can see the write of half of X, and here the write of the 2 halves of Y. Something to be noted is that those 2 writes are related by the SI same instruction relation. And that's a relation that we're going to very much use in our extension. And we've got the green arrows here that correspond to the defense instruction DMB that I've placed between the 2 stores. On P1, we've got a long load of Y, and at the end, a long load of X. In between those 2 loads, I've placed an AND instruction and a store of the second half of X. So the AND instruction is going to create an address dependency between the long load of Y and the short store of X. You can see it on the drawing here. I have arrows that correspond to the address dependency created by the AND instruction. Now, the short store of X, the store to the second half of X, is then read by the read of the second half of X that's created by the load of X over here. And so in the initial model, in the core model, the sequence of an address dependency and a read from relation provides an ordering, and which is depicted here by the green arrow from D to H. So the question we're asking essentially is whether the ordering can be extended to the other events that come from the same instruction. So here is the fact that those 2 sub-events to the 2 parts of X related by the SI instruction, does that mean that the ordering we've got from D to H also goes from D to G? And the answer is no, because that behavior, that the litmus test here, is observed on hardware and has been deemed to be allowed by ARM. So we can't simply extend the ARM model by extending the locally ordered before relations to all the sub-events of an instruction. So therefore, we took the other approach. We considered that mixed size accesses inherit the ordering that are due to communication relations. So our extension principle is as follows. If an event E1 is before another event E2 with respect to a global communication relation, then E1 is also before all the sub-events that are generated by the same instruction as E2. So in the formal model, it looks like this. So I've only extracted the bits that are significant in the CAD file. That does a lot more to see. So we've located all the global communications, so that's local write successor LWS over here, and observed by OBS over here. And we've sequenced them with the same instruction relation. So that means that if there was an ordering that was due to local right successor, now it extends to all the sub-events that are in the same instruction as the target of the local right successor, and similarly for observed by. The other column shows the English transliteration of the formal model, and that's what appears in the ARM documentation. Right, so now I'm going to show how we use the extension for Linux locref. So the virtual file system layer inside the kernel is responsible for handling system calls that relate to file system operations. And the kernel uses a hash table that's called directory entry cache or dcache to ensure that accessing file metadata such as permissions does not become a bottleneck. And to do so, accessing D entries is done using locref structures. So a locref structure, here's the little bit of C that corresponds to it. And a locref structure packs a 32-bit ref count and a spin lock in a line 64-bit word. This structure allows the ref count to be incremented using a 64-bit comp exchange without taking the lock. And this is where mixed-size concurrency can come into play. If one thread attempts a spin lock operation while another attempts a compare exchange to obtain the reference to the same D entry. And in such a scenario, it is necessary that either the comp exchange or the lock acquisition fails. So here's the litmus test that corresponds to that requirement. Consider a scenario where thread P1 has finished with a D entry and therefore drops its reference and indicates that the ref count is not 0, as we indicate here in the initial state. Concurrently, P0 is going to locate the same D entry in the D cache and is going to attempt to increment the ref count from 0 to 1 using a 64-bit comp exchange. So that corresponds to the compare and swap CAS instruction here that I've highlighted in yellow. Thread P1 then attempts to transition the D entry to dead and takes the spin lock using a 32-bit atomic operation that corresponds to the swap instruction here that I've highlighted in orange. And I would like to emphasize the fact that the swap here has an annotation A for acquire, which gives it strong ordering guarantees. It means that all the events, all the instructions that come afterwards in program order cannot be hoisted up. So now with the spin lock held, thread P1 is going to recheck the ref count with a 32-bit load, which is in pink here, to ensure that it is still 0. But for this protocol to work, it must be the case that either thread P1 observes thread P0 increment to the ref count, or thread P0 observes that the D entry lock is held and fails to increment the ref count. And before we did the extension, the undesirable outcome of the litmus test was not prevented by the architecture. In other words, the ARM specification did not give enough guarantee for this to work as desired. So to show what was missing, I'm going to show the execution for that litmus test. So this is the whole execution for the litmus test. It's a little big, so I'm just going to zoom in on the events that correspond to the instruction we're interested in, the ones that are highlighted. So here's the zoom. We've got here the semantic of the compare and swap or CAS instruction. In particular, we've got the two writes to the two parts of the log count that are related by the SI relation. We've got here in orange the read of the first half of the log count, again with an acquire notation because it comes from the swap acquire over here. And we've got here in pink the read that comes from the 32-bit load, so the read of the second part of the log count. So now let's have a look at the communication relations and the ordering relations. The swap, the read that comes from the log count takes its value from one of the writes that come from the compare and swap. So we've got read from arrow here. That's a strong ordering because it's an observed by relation. So I've made it green. Then we've said that the acquire has strong ordering properties, and in particular, it orders all the events that come afterwards in program order. So we've got, again, a strong ordering in green, a locally ordered before relation to the pink read here. So now that pink read takes its value, the value taken by that pink read is overwritten by the other write of the CAS. So again, we've got a green, a strong ordering relation, an observed by relation. But you can see that there's no green cycle. I've got a hole here in between the two rights due to the cas. But we've added the fact that if I've got an ordering, a strong ordering, so that green arrow here, that's followed by a same instruction relation, we've added the constraint that this is now ordering as well. And this is what the blue arrow represents here. Due to the mix size extension we're proposing, we've got a strong ordering from the pink read to this yellow right here. And now we've got a cycle. The blue arrow and those two green arrows form a cycle that forbids the undesirable outcome. So this is it. This is a bunch of extra material, how we use the tools within ARM and ongoing work. That's all for me. Let me know if you have questions.
Okay, we have time for questions, and we have people who want to ask questions.
Are you going to ask the questions out loud, Andrew? Or?
Yeah, I'll start off one. This is James Riley from DePaul in Chicago.
Hi.
And yeah, I had a question about the alternative characterizations, actually, which you didn't talk about. I know one of the goals of those is to make reasoning as local as possible within a thread.
Yeah.
And, when we were trying to work with that, the thing that frustrated us a bit was the fact that the semantics distinguishes reads that are fulfilled locally from reads that are fulfilled, remotely. So the RFIs versus the RFEs.
Yeah.
And I just wonder if you have any comment on that.
So the alternative formulations, I don't find them easy, and they're not easy exactly for the reason you mentioned. We have to talk about what in hardware terms corresponds to forwarding stores, and the crux of it is exactly along the RFIs. So I think what I'm trying to say is I share your frustration. It makes the equivalences and the formulation themselves fairly tricky, I find. But my observation from working within ARM is that it speaks to hardware people very much. They recognize those concepts much more than I could, because for me, they're just abstract semantics concepts. For them, it speaks to them very concretely. So perhaps the frustration is, to an extent, alleviated because it has a very concrete meaning for hardware folks. Does that answer your question at all?
So well, the commitment to the distinction between RFI and RFE, that strong commitment, it comes from the behavior of the pipeline, I suppose.
So I don't know about pipeline because, again, I don't know enough about concrete hardware, but
Right.
certainly it comes from that's
somewhere.
what speaks to hardware folks. Yes, they recognize those concepts very much.
Okay, thank you.
You're welcome.
All right, and in complete shock to nobody, I'm Alan Jeffrey from Roblox, asking the next question, which is that it seems like there's a tension between the constraints that ARM's placing on the hardware developers versus the guarantees that the compiler writers can depend on, software writers can depend on. And it's interesting seeing where this lands on various bits of the specifications, like MCA. Yay, right, okay, that's a constraint that's been accepted.
Yeah.
But on the other hand, something like, there's no control dependencies between reads. That's something that would be nice for software developers. And from the outside, this seems to be a bit of a random number generator. So I can't tell what the design decision process is for that. So I was wondering if you could comment a bit on that.
So it's not random. You're very right that there's a lot of tension between those two worlds. And actually, this is part of my job to try and understand what the requirements are and reconcile the tensions as much as we can. One thing I would like to mention is we've done a lot of work on dependencies in the last years. And there is a tech report that I can send along if that's of interest. We've tried to clean them up quite a bit. And we're looking for feedback along the lines of the one you've given. So, sorry, I've lost my train of thought. Yes, so the reconciling those tensions. there is one thing that we can't do is once somebody has implemented a machine that exhibits behaviors, we can't backtrack and strengthen the architecture retrospectively because that would invalidate their design. So perhaps this is what looks random is we know, for example, of partners that have implemented certain things, and that means some strengthening that we know would be valuable to the software world, and we would like to do if we were free to do so. We're not free to do so. Does that make sense?
Cool. Yeah, thanks. Oh, and it's a really nice bit of work. So congratulations on that.
Thank you.
Okay. I think maybe we should move on to the next talk in the interest of time.
All right.
But, thank you very much.
Thank you.